Organization. Okay, so you will have free lunch, but there's nothing like good lunch. Somebody will pay, but somebody will pay. So in order to collect the money from the person to pay the lunch, 10 people, 10 elected people from you should sign the rest.
Not from ICT.
Not people from IFT, but because this is like money. So people from outside the IFT, preferentially professor because they get more money, and then we go down. Or students that get money. But I mean, you sign it, you receive money, but you won't receive money to pay lunch. Okay.
You're doing pro bono work.
Exactly. Okay, this is one organizational thing. The other organizational thing is that we will better this currently. So there will be one more before the end of the semester, and then next semester will be 3 or 4, and hopefully this to take off and we have it speak forever. And the other thing is that please get involved in the organization. So we just keep it on, but we don't want to get it off all the time. So the idea is that you suggest speakers, which you can suggest yourself as a speaker, suggest large speakers, provided they are free, of course. And so we are open, we don't have any slot for next speaking, and we don't have a fixed date for next speaking, but it will be sometime in May. Okay, so maybe before we start with the first talk, we go just go around, everybody says 10 seconds, 30 seconds who he is, she is, I mean, what is the level, professor, master, student, whatever, and very broadly, what is the area of interest. Let's start from here.
Hello everyone, I am Louis Lebron, a postdoc at CTP, and I work on the CMP computational lensing, and also on the correlation of the CMP with galaxy service and galaxy stuff.
Hello everyone, I'm Isabel. I'm a postdoc at IFT. I work with CAD. I do gravitational waves mostly. Technology with gravitational waves, especially gravitational.
Okay, so I'm Balkan Gilbert. I'm a new postdoc here in the ICTP, and I work mostly for galaxy surveys, in particular the Lagrangian survey and LSST right now. And my main interest is trying to look for remote Lagrangian entities in the galaxy.
Right, so who's the grad student? We're going to show how long.
You are
From
you are on Cosmo.
yeah, I'm studying this in Walsh.
First, when did part in my master is which work with mock simulations.
Got it.
Yeah.
From Paulo, and work with function tracer and large scale structure.
So PhD students and Professor Paulo and I work with students.
So hi everyone, my name is Natalie. I'm a final month PhD student. So mostly I try to do cosmological parameter wave inference using machine learning and a bit of Halo Galaxy connection, working with Paulo, and I think that's it. Yes, I am Natalia, a PhD student, also a whole student at the University of São Paulo. And I work with machine structure and applications of machine learning cosmology, like Quasar classification, Halo Galaxy connection.
Nicholas, I'm a PhD student at the Federal University of Isaiah under Professor Intl. I work with quantum theory of spacetimes and in particular holography in non-NDS spacetimes.
Hello everyone, my name is Jose, I'm from Peru. I am a master student and I do my master program in Mackenzie Presbyterian University. So I'm in another research field. To me, it's very interesting. I'm working about the effects that space weather in the lower ionosphere.
So hi, my name is Ron. I'm a PhD student in IFT, UNES. I work with Phys, and my work is about observational cosmology, more specifically analyzing non-standard dark energy models to solve cosmological tensions and anyway, just explore games.
Hello everyone, my name is Isabel. I'm from USP.
and I just finished my master's and starting the PhD right now. And I work with scaling relations in galaxy clusters.
Hello, I'm Lucas. I'm an exchange student, master's level, working with Raoul from the Uppsala University in Sweden. Currently doing a very small project about quasars in the Gaia survey.
Hello everyone, my name is Rodrigo. I'm a postdoc in the IPC in Spain, and I work mostly with theoretical cosmology and simulations.
Don't say anything.
Okay, so I think we can start. I mean, you already introduced yourself, so it's very convenient that you were the last. So you can also introduce the student here.
Yeah,
Is visiting for,
no, yes.
Yeah.
I worked with Marcus Miller. I did my master and PhD with Marcus. First question. Anyone knows how to put full screen here? You can figure out? No, I can. I don't find it. Yeah, please.
okay. There is a link comment. We will introduce ourselves. So,
Yes.
yes,
Hi everyone, my name is Gabriel. I'm a master student at IIT. I work on Eureka. So,
yeah, Gabriel, please go ahead.
yes, so my name is Gabriel. I'm a master student at IIT and I'm working on Eureka. I'm studying gravitational waves. That's it.
We should chat to each other.
Hi, my name is Laerte and from Yazoo.
One more.
So we just all introduce ourselves. You're the last one, so.
Okay, my name is Leonardo. I'm from the University of São Paulo. I am a PhD and PhD student. And I'm here to see what's going on with physics in Astro. And I work with lensing.
Awesome. The number stabilized. Okay, so let's say 45-ish plus 20. Yeah.
Okay, yeah, please feel free to escape, try to take time. That's more informal. So, okay, yeah, today my idea is to talk about different subject. So I completely changed the title and my presentation for today. Sorry, because I think that most of you were in the EFT the last week. So today I need to talk about how to use continuous normalizing tools for simulation-based inference, particularly in cosmology, of course. So the idea is to be more introduction to the subject. So I start to introduction to simulation-based inference in general. Then I need to move to introduction to continuous normalizing flows. I don't know how familiar they are with this subject. Then I go into application of the continuous normalizing flows to the simple case of a Gaussian based field. And the last thought is about how to put something more realistic, like Galaxy or actually any tracer, and how to run all the pipeline with some tracer. Yeah, right. So let's start with the basics of inference. So the whole idea of any inference is to compute the posterior PDF, which gives the probability density of some parameter, giving some observed data and some model, right? So we want to get this guy here, and because of the bias theorem, we know that we can get this PDF from the likelihood times the prior, times the normalization. I will not talk about here. But we can also Yeah, so the posterior from the joint distribution, which is usually not used in cosmology, but we will see that with the simulation-based inference, we can actually compute the joint distribution. Okay. So these are all elements in the usual inference. And for this talk, the most important ones will be the joint, the posterior, and the likelihood. Okay. The prior will be it's very important, but will be the same of the usual experience. And the Bayesian evidence is also very important if you want to compare models. But here I'm not going to talk about this. So because of the bias theorem, as I said, we can just assume a likelihood and use this likelihood to get the posterior using, for example, a CFC. So for the likelihood, we have to basically have three main elements here. The first one is the likelihood itself. We have to assume something for this likelihood. The most usual function that we assume is a Gaussian. This is because of the synchrony limit theorem. Okay, so we don't really know the likelihood of the observations, but in the assumption that we have many different realizations that we are taking the average, we can just take a Gaussian. The second thing that we need is some model for the observed data given a parameter and the underlying model. Okay. For this, we can take either a theoretical model, like I don't know, like 10 or something like this, or you can use emulators from simulations. For example, HaloFit for the nonlinear matter power spectrum. Okay. And the last component is the inverse covariance that we also need here. It's also a function of the parameters and of the underlying model. And for this, we usually use some fast simulation, for example, like sales, compute this covariance for some observable. Okay, so we need these three main elements here, and the likelihood is usually the main component of the inference. Okay, but if you think better about the likelihood, we see that the likelihood is the same thing of our simulator, right? Because the simulator is just something that you put some parameter and some modeling and get some realization of the data. For example, we have any more simulations. It's just a likelihood, okay? It's just an implicit likelihood. Because you put your cosmological parameters, you're modeling like the Newton gravity and get the final density grid, and you can also, I don't know, measure spectra, measure the bispectra, and measure anything that you want, and get some realizations that have some scatter. Okay, so it's the same thing of the likelihood. And you can also see that the other two components of the likelihood here, the model and the covariance, you can also get from the simulator, which is the likelihood. It's just the expectation value of some measurement, which is some data. So the point here is that the simulator is everything that you will need for to run an inference. Okay. So going back to the Bayes theorem, so the idea of the simulation-based inference is to try to emulate using neural networks usually some of the three PDFs here. Okay. The first thing that you can do is to emulate the joint distribution. So you want to model the PDF of the pair of parameters and data. Okay. And at the end of the day, you want to take a slice when the data is equal to your observed data. But the problem here is that you have a high dimensional PDF because you have the combination of the dimension of the parameters and data. And also you have to take this slice usually in a high dimensional space. One way to do it is, for example, using the ABC, which is the approximated bias computation, Bayesian computation. But it's very hard and usually it's not feasible high dimensions. The second way to do it is to directly emulate the posterior. This is very good because it's the sequence that we want to get in the end. But the main problem here is that you are restricted to your prior that you have used it to generate your simulations. Okay. And the last thing that we can emulate is directly the likelihood. And this is good because we are independent of the prior, in this case, but we have to run some MCMC to get the posterior as we did here in control analysis. Okay, so those are the three main ways to get to the posterior using simulation-based inference and specialist neural network. Of course, you can use some other methods like ADC, that where you don't need neural networks. But neural networks, I think that's the standard now.
So, Rodrigo,
Yes.
your last point. I'm not sure that this is true because the prior is implicit in the simulation.
Yes, if you are trying to, for example, to fit
But
for
I mean the left. You said that this method is independent, right?
yes.
Actually, it is not, because if you are using the simulation that it right. That's my point.
It's independent in the sense that in the end of the day, you put it, you change the prior. The prior here is so important for you to get a good resolution in the regions that you want, right? To get a good fit of this expression as function of theta in the region that you really want the parameter, right? But we should just completely change the prior that you have used it to generate this relation. But it's not the case for the joint coordinates field. For both cases here, you cannot change the prior that you have used it to generate the relation. Right? That's the point. That's it. Okay, so I hope I convinced you to do why to do simulation-based inference. Basically, the main point is that all information that we know is in the simulator. Okay, there's no reason to not use just the simulator, and no reason to not use all the information in the simulator. Okay, because usually we don't know the likelihood of the problem. Even for the power spec, we don't know the likelihood of the power spec, right? We usually just assume a Gaussian, but we know that's wrong. Okay, especially for low K, we know that's not a Gaussian and might have some problems. For example, when you fit, I don't know, things that are important in large scales, for instance, okay. So it's important that the likelihood is not Gaussian, even for the power spec. The second point is that the likelihood is also very expensive to compute, actually, right? If you think that you have to compute something like the model and the covariance for each parameter, it's very, very expensive if you want to compute it properly. So it's not really that you are not really saving time using some likelihood. The fourth point is that the likelihood, if you want to do something like AMCMC, you have to compute the likelihood on the fly, right? Because to move in the parameter space, you will need to know your current position in the parameter space. That's the deploying of Monte Carlo Markov chain, right? And with simulation-based inference, you can just run many simulations and use this data to train your PDFs. So it's better to handle this data. And the last point is that usually with our simulation, we don't use all information that we have in this simulation, right? We usually just use the mean value and the covariance, basically to compute the D and C here, right? So, and again, we know that the data probably has more correlator, more adequate functions, right? About the covariance of the mean. Okay, so any questions so far?
So I think I'm still a little confused of how do you use your simulation practice, right? So it's not, you will not compute any summary statistic nor anything, right?
Oh, you can. You compute. Yeah. The simulator here, you can think like, for example, in cosmology, you could think like the N-bar simulation plus some lifecon plus some estimation of CLs.
Yeah.
So the CLs would be the D, right?
Yes.
And the simulator is the whole process, not just the N-bar simulation, but also the process of measuring your particular summary symptoms.
So the thing is that I don't see the difference on computing just 1,000 simulations, measure the CLs for each of them, and then you use like usual likelihood, right? I don't see what's the difference now. I'm really confused. Sorry.
Okay, yeah. I think that the main difference here is that the usual likelihood,
Yes.
you have to assume a likelihood, right?
Oh,
In the simulation, you have at least likelihood that it's more reliable, right? Than
Okay.
the Gaussian.
But you will still compute summary in practice. You will still compute summary statistics over the simulations.
Yes.
Okay.
Yes. In next slide, you show that you can actually use the whole density field. Well,
Okay.
Yeah, I think I had kind of the same question. At the end, in order to evaluate, I mean, suppose that you have a well-behaved probability that has a minimum, a maximum, sorry, right? So in order to evaluate the uncertainty of that estimation for whatever model parameters, you need some metric in that whatever space that you have there. That metric is in some sense, you have to choose that. You can choose to be whatever you want, but you need a metric. Otherwise, you don't know how well you're fitting and how bad you are as you move away from that best fit. So when you do that, you have to assume some metric, and God knows what could be something which amounts to be just the Euclidean metric, which is what you call a likelihood, right? So how is it that you're not trading 6 for half a dozen when you're doing this?
okay, yeah, the point is that the metric here is very natural. By metric, I'm saying that I want my PDF and these three guys to be equal to the true PDF. That's my metric.
Good.
Yeah, the point is that I don't know my true metric, my true PDF. Yeah, but I sampled for my true PDF, right?
Sorry, no, I don't follow. What is it? How do you get a true PDF if you, like in principle, if you, unless you're imposing some prior on models and parameters that tell you that, this is what the matrix is beforehand. How do you know that? If, sorry.
Yeah, I think that I'm going to go back to this point. So in maybe 3 or 4 slides, so we can come back to this discussion. But yeah, that's a very important point. Okay, so yeah, so now let's move on to the continuous normalizing flows. And okay, we decided that we want to do simulation-based inference, but how to do it? And with neural networks, we should use. So why to use continuous normalizing flows? Okay, first of all, why to use neural networks? Because we know that neural networks are universal interpolators, so I don't have to assume any shape about the PDF. So it's very nice, right? And we had a lot of models for neural networks. The second point is why to use this specific category of neural networks, which are the generative models, okay? And the point is that we only have samples of the likelihood, okay? We don't have the actual value of the likelihood. So we are not trying to interpolate the likelihood like we do in a usual interpolator, like for the power spectrum, like Hill. We have the value of the power spectrum for HK, and we interpolate this. Here, we basically just have the case, right? That follows the distribution of the power spectrum, this looks like this. So for this, we have to use generative models. And explain more of these 3 last points here. And one choose specific normalizing flows, which is a class, which is a model inside the generative models, is mainly because normalizing flows can get the explicit values of the PDF, which is very useful, especially if you want to emulate the likelihood and use it to run a CMC. And also normalizing flows have a great occurrence for the PDF to describe the PDF with the line. And the last point, why is you using this continuous normalizing flows, which is a improvement of the standard normalizing flows, which is, I show that it is mainly because it is more expressive than the usual normalizing flows, because the usual normalizing flows have put many constraints in the architecture of your neural network. Okay. So let me talk about the generative models. What's the idea of generative models? Is that we only have a set of some variables, some parameters, something, and that were generated from a true PDF, and we want to recover the true PDF. Okay, but we don't know the value, for example, the value of the PDF for each value of the variable. We only have a set of variables. So the idea of this kind of models is to try to, or implicitly, either explicitly, get the PDF. So if you have the PDF, we can just generate new samples from this PDF. One very famous example is in the image generators. For example, the DALI, which is a diffusion model, which is a class of generative models. We can just start from some latent space, which is just white noise, in this case here, just Gaussian noise, and applying the technique, get some images. Okay, so we know that for images, this class of models very powerful, and the idea is to apply something similar for simulation-based inference because we have basically the same problem. So I think that here I can explain the questions that we had. So what's the point in cosmology? Okay, so first of all, we have to sample parameters from a given private. Okay, if we have to know this private, have some idea what are the good parameters that we want to look at. Then, given the parameters, we run our simulation, which is just our implicit likelihood, okay, which is the same thing. Here with sync, but it's the same of like the previous slides. So in the end, we have a set with the parameters and the data, which might be, for example, the color spectrums, the CLs, or anything. Okay, so with this set of parameters, we run the neural network to implicitly learn one of the PDFs. Okay, and with one of the PDFs is anything that we want. I don't know if it explains or not. And here is the point that how we compute what's the method, what's the loss function. Okay, it's just the difference between the chiral divergence between the true PDF and the PDF given by the neural network. But because we have sample from the true PDF, we don't need to know the true PDF. It's the same technique that we use in, for example, in MCMC, right? Because we are making the average over the sample data from the PDF. So the PDF, the true PDF is implicitly given. So we don't need to really know the values of the PDF. So the loss function is just the log of the likelihood predicted by the model, which is proportional to the chiral divergence. Yes.
So this is like normalizing flow that you have, two distributions of two different things, and you map between them, and there's a mapping internally, which is whatever nonlinear. It doesn't have to be Gaussian, and this is what you're calling the distribution, that way that you can go from data to parameters and back. So your P of the parameters in some sense, as you map from the data to the parameters, you learn that mapping. That's what you say. That's what you mean by there's no intrinsic putting by hand. You're just assuming that the code that the machine learning behind it learns this mapping.
Sure, it's
well, you have used a certain.
The PDF is the PDF. The transformation is the transformation. Separate.
Yeah, but then what is the PDF in that sense? I mean, you have chosen a certain set of parameters, which is your initial parameters, right? And you just produce simulations on that, right? So you have a kind of a many realizations with many different values of the parameter. Then you have your data. Then you ask, what is the likelihood of the parameters or the probability for the parameters for a given set of data? right? So you have to know how to map that point back to a kind of a cloud here in parameter space. This is what normalizing flows, for instance, does, right? So that mapping is the probability of the parameters giving that data. Yeah, so this is what you mean that this mapping, you're assuming that the code knows how to do and it doesn't assume anything. That's
Yes.
all right.
Okay, let me just talk about the loss function here. This is just the chiral divergence. So we have the chiral divergence between the neural network PDF, which is a function of the parameters of the neural network, and here we have the true PDF. Okay, let's say for some variable X.
Sorry, so, yeah, I think I'm still confused what do you mean by PDF here in this context? How do you obtain the PDF from simulation, from one person?
From simulation.
See,
Yeah, you take the parameters from the prior,
yes,
okay?
yes,
Then you take the data from the lighting, which is the simulation itself.
yes. A three-dimensional simulation from,
Yeah, anything, any kind of simulation. You want.
okay,
For example, a bar simulation.
like on paper. Okay,
Yeah, so now you have this pair of parameters and data.
yes,
So from this, you can get a lot of parameters and data, okay? Let's say n of this. Okay, you run the simulation many times.
yes,
So you have many pairs of parameter data.
okay,
And with this, you have basically sample from the joint version of parameter data, right? The true joint.
Simulation.
Yes, I assume that my simulation is the truth.
right,
Good. So here I have sample from the true joint. That's the idea. So I know because of the points that I have here, I have some information about this distribution. Okay, so the idea is to compare the distribution given by the neural network with the true one. This is just, we just take the chiral divergence, compare two functions, and the string given, because we only have n. Yeah, this is basically something like the true distribution times the log of the neural network minus the log of the two. And of course, here is the function. Right. This guy here is not important because it's not a function of theta, so the correct answer is 0. And this thing here is just the expectation value of the log. Where I took this expectation value with respect to the true posterior, right? So my loss function is just the expectation value of the log of my predicted PDF.
So I understand the right hand side, but can you see this telling what the loss function set for the left side? You are related the loss function to the PDF. But so what does the loss function represent?
Represent the difference between the two PDFs.
The mean sort of mismatch between
Yes.
the model and the
If the two PDFs are the same, this is the one.
okay.
You say that you're using some narrative to do like a kind of interpolation of your PDF between the points that you sampled.
It's not, it's kind of interpolation of the PDF, but not in the usual way, right? Because I don't have the value of the PDFs. That's the difference of the generative models. It's different from a usual emulation.
You have sampled PDF in some points, and then in the narrative, you want to know what is the value of PDF outside of these points.
No, actually, I want to know the PDF. Or more specifically, I want to know how to sample from this PDF. This PDF I don't know, right? I only have implicitly in the simulator. So I want to be able to learn this PDF. For example, here, right? What's the PDF of cats playing chess? Don't know, right? It's a very complicated PDF. But if you train these generative models, we are able to sample from this PDF, even without really knowing the PDF. So here's the same thing. I want to be able to sample from this PDF, even without really knowing this PDF. For the normalized flows, it's especially good because I can actually know the PDF. So it's why the normalized flows is a better generative model for this application. For example, the diffusion model, like the one here, we don't have access to the values of the PDF for a given data. Okay. So that's the idea how to do it in cosmology. I don't know, sure. Yeah. So just to summarize the generative models we have, those four are the main models. Okay. The first one, which was the old standard, was the generative universal networks, where the idea was to train one network to generate an image from noise, and another network to discriminate if this image generated by the first network was a real image or a fake one. So the idea is to put both networks to compete and to get better at each iteration. This is very good, but of course we don't know that the PDF here is completely implicit in this case. A second option is to use variational autoencoders, which is a variation of autoencoder, okay, where we have an initial image or initial data here that we respond to a latent space which is much smaller. Then we have a decoder that go back to the original image. And the idea of the variational part is that we constrain the distribution of the points in this latent space to be more compact. So it's easier to really generate images. And we also have the diffusion models, which is the one that generated the cat. And the idea here is to start with an image or a data and apply a Gaussian noise in each step till we have basically only noise. And then we train a neural network to basically remove the noise of the image. So in the end, you can just put some noise, apply the neural network, and take some image that makes sense. And the one that we are going to use now is the normalizing flows, okay? Flow-based models. And what's the idea of the normalizing flows? The idea is that we start with latent space, with variable latent space, which usually is just sampled from Gaussian. Then we want to apply some transformation, that is the neural network in this case. Theta is the parameters of the neural network. So we want to apply this transformation to move the points here to the space of X, such a way that now the distribution of X resemble the true PDF that we want to get. Okay. So for normalizing flows, the trick here is to use the composition of many simple functions. Okay, so we also need to know how to invert this function, which is the inversion of each function here. And because of the change of variables, we can explicitly compute the final PDF. Okay, the final PDF is just a function of the base PDF, which is a Gaussian, that we know how to compute the log of the Gaussian, plus the determinant of the Jacobian state transformation. So here there are two very important points that we need to know how to invert the transformation. It's not trivial from neural network. And we also need to know how to compute the determinant of the Jacobian, and we need to compute it very fast, okay? Because we need to compute for each step in the training. So one way to accomplish it is using, for example, the masked autoregressive flows. With the idea is that we have the Latin space here. So each point of the Latin space is mapped to the next layer, okay, or to the final here, X. So each one of this transformation is going to map this to this in a linear way, where the coefficients of the linear transformation are given just by the previous parameters, the previous components of the variable. Because in this way, you can see that the Jacobian is triangular, okay, because this guy is completely independent of the guy that comes after it. So the Jacobian is triangular, so the determinant of the Jacobian is just the product of the diagonal. So it's very simple. In this case, that you assume that you have like an exponential of alpha, the log of the determinant of the Jacobian is just the sum over the alpha. So it's trivial to compute the Jacobian. And it's also, of course, trivial to compute this because it's just a straight line. So this is the masked autoregressive flows, which I think that's the standard way to normalize the flows. But you also have other options, okay? The main point that you really need to address here is to make the Jacobian to be trivial. That's yeah.
How do you compute the alpha E and then?
Yeah, this is the neural network, okay? Alpha E, for example, for X, to compute Xi, the alpha I will be given by the as function of all X's before I. So from 1 to I minus 1. So you have a neural network where the outputs are kind of the name masked here is because the neural network is masked. Such way that the outputs here, for example, the first output is independent of all inputs here. The second output depend only on the first input. The third one only on the two first. Okay, so you have to put a lot of masks in the neural network, and to get this triangular Jacobian. Okay, so it's the alpha and B is just neural networks, the outputs of the neural network. Okay, any questions so far? Okay, now what's the continuous normalizing flow? Okay, the continuous normalizing flows follow the same idea, but now we, instead of doing like K transformations from the linear distribution, we do K transformations. Now we basically do infinite null transformations. Okay, so we have now solve this ODE here, where now the neural network is not the transformation itself, but is the vector field that gives the transformation. Okay, this is basically what's the name? It's a neural ordinary differential relation. So the same thing that we have here, the change of variables for the PDF in the continuous case is also given by another ODE. So in the end of the day, you have to solve this system of ODEs, one for the trajectory that goes from your Gaussian to your final PDF, and one for the PDF itself. Actually, we solve backward because it's simpler, because of the initial conditions, because we know that in the end, the variable must be equal to your variable, your data, and the difference between the PDF is just the true and the final. One should be 0 because one should actually go over. Okay, so we have to solve this, but now F here is a neural network. But the main point here is that first of all, the inverse is trivial because it's a first order ODE. So the solution is just the integral over the vector field, and the inverse is just actually to the other side, which is integral. So here is the inverse, and also this term here, which is the trace of the Jacobian, it's also trivial to compute using this trick here, that the trace of a matrix is just the expectation value of epsilon times A times epsilon, where epsilon is a normal variable. And this is faster than computing this trace because of the auto differentiation that we can use for JAX or PyTorch. Okay, so because of numerical facts, we can compute this trace also in order n. The same way that you could compute this trace in order n. Okay. So here we have how it should work, right? We start from a Gaussian in t equal to 0. Here the times is meaningless, okay, it's not feasible. And I have some vector field that's given by the neural network, and we want to go into this the diagonal PDS. So here is a git how it works. Okay, hope you can see. But basically, this is the target PDN. So it's just points that follow this distribution, which is basically 1 in the cat and 0 outside. This is just the GitHub cat. So we have just a sample of points here. Okay, we don't know the PDS. So we start here, just from a Gaussian, it's basically a sphere here, and following this vector field that, of course, evolves with time, we can get a very similar distribution of points that we have for the target. And because we are using normalizing tools, we also have access to the PDF itself. So here you have the values of the PDF, and here a sample from this PDF. So, yeah, that's
Target is your simulations.
yeah. For example, yeah. Here is a very simple, just a 2D data, just an image, just following. But in for cosmology would be the parameters. So, okay, the main advantage of the continuous case in contrast to the discrete case is because it's much more representative. It's more it's stronger. Okay, it can reproduce better the distributions. Why it happens? If in discrete case we saw that the transformation would be something like this, okay, where the component y at some iteration t plus 1 would be given by the component y in some iteration t times this alpha function, which is just a function of z up to I minus 1, okay? And the same for me, which is how we make the Jacobian trivial to compute. But now for the continuous case, to use for the first order Euler, just to get some information, we see that at order t, t plus 1, sorry, it depends on all the vector at order t with a very complex neural network here. And here you can see an example, okay? We have 3 examples of distributions here. This middle column is flow is just a usual normalizing flows, and fjord is the continuous normalizing flows. And you will see that the continuous normalizing flows is especially good to reproduce the tails of this that are rolled here. You see that again, especially in this case here, we have much better behavior for the tails, which is very important for some statistics in cosmology, for example, the test, where the tails are actually the hard part to describe. Okay. So just a quick thing that I don't have much time. So basically the number
We are flexible, but just so you have an idea.
okay, the number of functions evaluations because we have now to evaluate the neural network many times, because we have to solve the ODE, with, for example, or something like this. But one thing is that the number of function evaluations is not a function of the dimension of the problem, which is very good. So we can go to very high dimensions that, and we don't need to compute more times than the vector field. And this is just a technical thing that you can also apply this polynomial regularization to make the vector field simpler. this increases a lot it speeds a lot all the process because now the OD solver can make larger steps, okay, because the derivatives are smaller to find derivatives, and also it's better to avoid overfitting.
Brilliant. So since you're trading the, let's say, in order 10, you have to run 10 epochs of discrete transformations. Here you say that your order is now not 10, but let's say you have a polynomial of order 10.
Yeah.
That is essentially,
Yeah.
you're trading that sense, right? You don't have the epochs anymore. You're just fitting for these 10 parameters of the continuous fit.
No, you have the epochs for the training the neural network.
Okay, but you don't have the 10 discrete transformations. That since you have when you have a polynomial of order 10, it will be equivalent to the same number of parameters at the end, right?
So
How do you find those? You do have a kind of you are saying that the function that you're fitting has to have some form, or do you leave it completely open?
No, it's completely free.
Sorry, then I didn't understand the example there of a polynomial.
This is just an extra term that you can put in your loss function.
Oh,
In addition to your Kaelo versions to make the vector field simple.
okay, then.
But you are completely representative of your problem.
Okay, so then
What
I understand that is that your vector field has in principle infinite parameters. How do you fit that in each epoch of your training?
the parameters of the vector field are the parameters of the neural network. You just run a gradient descendant over the longitudinal or the OT solver, okay? Because at the end of the day, you have to discretize your OT. You can just, for example, for this is a possible solution of the ODE, right? So here you would just run a backpropagation here because you have your neural network and you know how to go from one step to the other. But of course, you have to backpropagate harder 1 2 times. So it's of course not more complex than in this case. So yeah, this is just a concrete example of how good this is to reproduce some PDF. This is the 10-dimensional completely run PDF that I just painted. But you see that the red regions are the red curves are the data, and the blue ones the ones recovered by the conditional normalized the continuous normalizing flows with just I don't know 10 apples and with just 1,000 data points. So it's really good to basically reproduce any PDF with any here. So another thing that's good to discuss now is that I just took this example here and take the two first components, condition them to the other 8. So now I try to compute some conditional PDFs, and here's just to show why the joint is not very good. Here the 3 colors here, I'm just taking the joint PDF and try to use ABC to make that slice, okay? Because to get the data, I need to make a slice, and to make this slice, I have some widgets for this slice, right? But the problem here is that I have to make a slice, and I use dimensional space. It's not very large, but still we see that the convergence of the final posterior is very, very slow steps. And these red regions are really very expensive to get. So using some conditional continuous normalizing flow, which is the blue region, it's
Sorry, conditional what? What? Sorry.
here is the condition. We are trying to take the PDF of the first 2 dimensions, conditional to the other 8. So a very simple example. But just to justify why I'm going to use the conditionals for the function. Okay, it's just to talk about very quickly about the condition, but it's just the same thing, but now we have to put some extra conditions y. But it's the same problem, and now the original PDF is also conditional by this condition y. For example, in cosmology, that would be the cosmological parameters, and y would be the data, like the force spectrum, the density grid, or anything like this. So here just to describe the architecture that I'm using for this continuous normalizing flows case. So we have these concatenation layers, okay? Basically gets the output of the previous layer here and some conditional, for example, the density bridge or the core spectrum are the two things that I tested, and also get the time, okay, because the vector field is also a short time. So I pass the condition to some neural network for the grid convolutional one for core spectrum just a multi-layer perceptual. And then I concatenate with the output of the previous layer, pass to a multi-layer perceptual, have some output that I multiply by the time passed by a multi-layer perceptual, and with the time passed by another multi-layer perceptual. Okay, then now I have the output of this layer, and I combine many of these layers to get my vector field at some time t. If for some parameters theta and some conditional for the grid or the core spectrum. So the conditions that are entering in each layer here, not just in the beginning, which is how you usually do for the usual normalizing flows. Okay, very quickly. Okay, so I run some Gaussian fields. This is the likelihood of a Gaussian field. It's not a Gaussian. It's very nice because you can see here that the Gaussian is not exclusive. So when I compare the units MCAC with the continuous normalized flow, that SPI both give basically the same posterior with respect of the TMC with the exponential that gives a smaller posterior because it's actually the likelihood for the field. We can run for thousands of run the inference for thousands of realization because it's very fast. So then you get something almost a Gaussian here. Another nice property of this method is that if you don't train enough, we always get larger PS that are always not biased. So to train more, you get closer to true, but if you train less, you just get a larger error loss, which is fine. Right? Okay, you have this is more technical, but just to see that we have to apply some augmentations to the data because we have to impose the symmetries of the grid in the case of the grid here. And maybe this is slide that show that the results are very robust to change in the neural network. For example, if you double the number of layers for the compression, or double the number of layers to compute the vector field, or reduce the number of simulations used to train by a factor of 3, you basically have the same posterior all times in comparison to the deduction. So, okay, yeah, this is the hybrid that I talked about last week. But the idea is to combine this hybrid approach to generate the grids, okay, for the biased fields, and use it inside the continuous normalized flows to get the possibilities. But this is for the future. Here's just comparing with Paulo, showing that these emulators or the displacements that work better than Paulo. And okay, just to finalize the comparison, because there are a lot of other groups that are trying to do field level, first with field level. I think that the two main groups are the CND group, but the problems with the CND is that they have just a small number of simulations, just around 2,000. The simulations are very low resolution. They have about 1 particle per megawatt particle. They are using the usual normalizing flow, so they have to compress the data before running the likelihood, the estimation, the posterior estimation. So it's also not optional. And they also have a fixed stochastic part of the theory because they are in HNP. And if you go to the left field group, they are just using theory. So they are very limited by the scale and also limit the stochastic part of the theory. So yeah, that's it.
So I guess we can use 10 minutes for discussion if we move into the next topic.
Oh,
Yeah.
so can you like, just a really naive question, so where does the, for example, the errors in the covariance or errors in the estimation of the whatever summary you're using entering these kind of things? How do you know that you are not, for example, over fitting the parameters and have like way smaller error flags than you should from a realistic covariance?
The covariance is implicitly given by the simulator.
Okay.
So all the information about the scatter is in your simulator. So of course your simulator was the right one. Yeah, right, that's the case. It's always the case. And we have this kind of properties, these methods. When we go wrong, we always overestimate the errors. We don't get, it's not proven, okay, but maybe we don't get bias constraints and we don't get smaller errors, with the exception of overfitting, but overfitting you can control neural networks quite well in this case.
Right, so there is no way to put like an input covariance. Like, for example, if you have like a galaxy survey that has like a fixed covariance, you cannot.
No, we'll have to consider in later.
So you will have to construct something that looks like the covariance from the.
Yes.
Okay.
Yes.
So, coming back to this question, so let's say that you know exactly what the, let's say that you can find this, your distributions precisely well. Let me ask, maybe there's something that perhaps I haven't understood. So suppose that you have your set of real data, right? And this is your real data here. And of course, you can always find what is the maximum likelihood or whatever, maximum probability in this case, point that corresponds to this or the region around this. What I still don't understand is how do you go from that to quantify the uncertainty around this area in parameter space? You need to know, in some sense, when the probability is not, you need to have a metric for how far away you are from the peak. This is where it's not entirely clear to me that where it's coming from in this approach. Maybe I haven't understood something about this. I mean, you are always saying that you're finding the probability, but I mean, we're not talking only about probabilities. We're talking about distances between points in your parameter space and having a sense of how far they are. This is what defines your global probability, right? So this is what I still don't understand in this approach. By the way, I think it's a general question about normalizing flows, not necessarily about continuous normalizing flows. How do I assess the not goodness of it, the badness of it? I mean, when you are far from the best bit, where is this distance coming from in the end? Because I'm not seeing this anywhere, but it has to be somewhere. There's no a priori metric for this in this normalizing flows approach, right? But it has to be coming from somewhere.
Yeah.
Otherwise, you don't have a notion of distance in that sense, right?
Yeah.
Where is this coming from? Maybe this
From
is
the simulator. Okay, your simulator knows if one data is far away from another data, right? Because your simulator knows how to go from parameters to data. Your simulator knows how to go from one parameter to many data, and how basically knows the covariance, right? The covariance and also the higher and wider functions. Simulator knows everything, right?
Right. So you have to make sure that the resolution of your parameter space is then reflected into enough data points that you can figure out back when you move by this much, the data moves by that much.
Yeah, because the metric you are talking about is just the likelihood, right?
Yeah.
And the likelihood is just a simulation. So
Okay, I think I get it. Okay. I think I understood at some point, but then I forgot. And I was clear.
Then they have a sort of same question, but in more basic level, more naive, right? But I mean, in the Monte Carlo, I know that if I have a drawing, I prefer here, what I should do. the convergence. Once again, the simulator, what is, I mean, I really don't work. So I mean, really from a broad perspective.
Basically, I think that nothing, but because you are training a neural network to learn your PDF. Of course, if your neural network is too weak, we cannot learn your PDF or final PDF. You can guarantee that your neural network converts to a local minimum of the loss, but you cannot guarantee that it converts to the true PDF. And we know that's actually the case. For example, if you have just a small set of parameters, a small set of, you simulated just a small set of parameter data, you cannot really learn your PDF, right? So you convert to a raw PDF. But the point is that we observe that it always converts to a larger PDF. And the true PDF is always silent. So usually we are not biased, but it's again, it's not proven. It's just empirical constatation. But yeah, you not guarantee that you convert to your right PDF. But we hope that with infinite simulations and with infinite neural network, we should over it.
No, you're not going to, if you do, let's see, in the example you showed, you did 1,000 samples of your data. And then you run a few iterations of your neural network to try to get the PDF. I can be sure that you're not going to be overfitting if you do like an infinite number of iterations of your neural network, then you will produce only the data that you select. Because they don't have an infinite number of simulations.
Yes.
Can you show me the drawing?
This,
Yeah, like for instance, also very small filling dots, they are just because you have a finite number of simulations, right? And this not probably is a true PDF. So I can be sure that you don't go into overfit.
we are not sure, right? It's the problem that we always have with neural networks. We have methods, for example, I didn't talk about this, but for example, this augmentations, it's a way to avoid overfitting, you know. It's here is the log function. The red line is the log function for the validation. The red line is the case that I don't apply any augmentation. So you see that you get some decreasing and then this just diverge. So we are completely overfitting them for the training. The validation is completely wrong. But if you start to apply some augmentation, for example, rotation or shift it in our next degree, you see that the loss now gets better and better. And for example, the blue line is when you apply both rotation and augmentations. So now if the loss of the validation is better, means that probably you are overfitting less. Okay? We cannot guarantee that I'm not overfitting at all, but I can try to overfit less. For example, applying augmentations, or for example, applying dropout layers or just techniques of neural networks. You know? So I cannot guarantee that I'm not.
But yeah, last. Sorry,
I think that.
I just wanted that if you introduce. What's what the regular DPI introduce next year? That will just finish the out of this. You are not for that. Because in case you are sure that that word will overfit.
Yeah, you reduce the degree of overfit, right? But you cannot ensure that you are not overfit. Because even the dropout layers, you have to choose some probability of dropout. And of course, take this probability very low, you can overfit it. To take very high, you can overfit anything at all. So we don't know what's the best. We can try to get the hyper parameter, but it's always challenge.
okay, very last.
Oh, yeah. So you didn't mention nothing about like how to validate these things, how to validate these PDFs. And then what about for images? Do you have already any idea how to do this validation for image generation? because we know how to do with the PDF, so it's like the probability distributions that we have in this traditional ways, but what about for images?
Image, you mean general image like the cat?
Yeah. Because every time that we regenerate these fields in our case as cosmologists, we always try to see if you're right, going back to, I don't know, to power spectra or anything else like this. But how to really validate in machine learning like ways to do this? Do you have any idea?
General.
It's still it's an open question, it's just like I would like to know your opinion.
Yeah, I think that the only thing that I can think is using something like a validation test set, and try, for example, here you could try because you want to go from the get to the noise, right? So I can take my test set with some different images, go to the noise and try to come back, see if I recover the image. So something like the inspire error between the two images should be a proxy of the quality of my network. This case, or actually in the case of the generative models.
Yeah.
But of course, it's kind of arbitrary. Some number.
Okay. So again, thank Rodrigo again. Well, introducing your in 30 seconds. Update camera. Those who introduced themselves earlier, can do it now. You would like not going to introduce yourself. Just say your name, who you are, what you do this.
Yeah, I am as
Okay, so just like
Aqui, que acompanha solo da música, sou da graduação da física, e eu estou pensando no evento, estou aqui para ter uma visão de mais geral, sobre inovações e instrumentar.
beleza. Para mim.
Matheus, nossos estudantes, são alunos da São Paulo.